How's it going, everybody? Welcome to my channel. Today we have an amazing problem for you guys. We're going to be talking about minimum depth of binary tree, right? This is a very good problem from the looks of it, right? So let's see what it's all about, right? So it says given a binary tree, find its minimum depth, right? So the minimum depth is the number of nodes along the shortest path from the root node down to the nearest leaf node, right? Very interesting. A leaf node is a node with no children, right? So very clear and concise problem statement, right? So they're telling us that we're given a binary tree and we need to find the minimum depth, right? So, and they've given us the definition, what they mean, right? So the minimum depth is the number of nodes along the shortest path from the root node down to the nearest leaf node, right? So let's look at an example real quick. So they're telling us, right? So the depth is what they're saying, right? Is the shortest path from a root node to the nearest leaf node, right? So you can see in this example, we have many different leaf nodes, right? So, and a leaf node is a node with no children, right? So we know the definition of that, right? So what is the shortest path, right? From starting from the root, right, to any of the leaf node. The shortest path is obviously this one, right? That's why we end up returning 2, guys, because there are 2 nodes that are included along that path, right? You know, the path that leads to 15, which is a leaf node, right, is 3 nodes, 1, 2, 3, right? And this one will be 1, 2, 3 as well, right? This other leaf node, right? But we're looking for the minimum one, right? Which is the longest translating to the shortest path from the root node to whichever of the other leaf nodes, right? This is a very key thing to understand with this problem, right? You know, but we'll come back to it, right? So how do we go ahead and solve this, guys, right? You know, so they're telling us to find the shortest path from a root node, right? That's the translation pretty much. We're saying find the shortest path from a root node to a leaf node, right? And we need to return the number of nodes along that path, right? That leads to the leaf node, right? So that's kind of what the ask is, right? So now let's start talking about a kind of a solution that we need to do, right? So there are a couple of solutions that we could do, right? We know that we need to traverse the binary tree somehow, right? It's up to us to decide which traversal that we feel like doing, right? Do we want to do depth first search or breadth first search or whatever other traversals, right? A vertical order traversal, like, all depends, like, which one you want to do, right? So let's see, let's start simple. Right? I'm thinking that we could do some sort of depth first search, right? Start depth first search, guys, right? You know, we know it's we could write that recursively to make it very clean, very slick. We just loop through, start from the root node, obviously, and we loop through, and for every node we do +1, right? And then every node, right, we calculate the minimum depth of our left side or right side, right? And then we do +1 to account for ourselves, right? Because we need to account for that node, right? And then we return that to the caller, right? So 3 will call upon the left side, right? The left child, right? And then now we have 9. 9 would pretty much check it has no children, right? So that's going to be checked, right? So it's only going to return 1, right, to account for itself, right? So it does +1, right? And then, right, it 3 gets the answer back, right? And then 3 would then call, because 3 wouldn't know, right, if there's a shorter path that leads to a leaf node on the right side. So that's why it needs to go ahead and check, right? It needs to check the whole tree, essentially, because we don't know, because we're doing a depth first search, guys, right? So 3 checks on the right side and does the same thing. 20 calls on the left side, and 15 checks, no children, right? Return +1 to 20. 20 calls 7, and then it checks 7, returns 1 as well, right? It chooses the minimum one out of the 2, right? And 1 and 1 is the same, so the minimum one is 1, right? And then it does +1, it's again, right, to account for itself, right? Which is 2 now. And then now we go here, guys, right? So now 3 got 1 from the left side and 2 from the right side, right? So this side is a smaller path, right? So therefore, be choosing this one, right? And then that's why we end up returning 1 + 1 to account for the root node itself, right? And that's why we end up returning 2, guys, right? But you can see, this is a very good, solution, right? Straightforward, right? We could write it recursively, right? To do exactly what we want, guys, right? So let me show you guys the code real quick. So it has a root node, we check if it's null, return 0, right? And then if it's a leaf node, we return 1, right? We don't need to visit anything, right? And then we check our left side and our right side, and then we choose the minimum one out of the two, guys, right? Which is what we're doing here, right? Which is the minimum one, and then we do +1 to account for ourselves, and then we return that to the caller, right? Okay. So this is a very decent solution, guys, right? But can we do better, right? I think so. There's a little bit of, we could be more efficient, right? We could try out the traversal, right? Because we see we have to visit the whole tree, right? Because we don't know when to stop when doing that, because we need to visit everything to find the shortest one, right? The shortest path that leads to a leaf node, right? So, shortest path, right? So anything that, every time we deal with finding the shortest path to something, right? We know the algorithm of choice is breadth search, guys, right? This is it kind of screams breadth search, right? Trying to find the shortest path, pretty much from a source to a destination, right? And the source is the root node, and the destination is the leaf node, right? So we're trying to find the shortest one, right? So what we could do is traverse level by level, guys, right? And doing it level by level, right? We're gonna be efficient in the way that as soon as we get to a leaf node, we are done, right? We don't need to visit the remainder of the tree, right? We just visit that particular. We get to that leaf node, and then we're done. We return our answer right away, right? Because that's the shortest path, right? Because we are traversing level by level, right? It guarantees that the first one that we get to, that's a leaf node, must be the shortest path, right? Because we're starting from the root node and we're doing things level by level, right? So as soon as 3 adds each children, right? And then we are the next level, and we see this one's already a leaf node, right? We don't need to visit the remaining tree. We're just done, and we just return it, the depth of it, right away, guys, right? So the code will be very simple. Let's quickly go ahead and do the code real quick, okay? So I'm thinking we're gonna use a queue, guys, right? A queue of what? Of nodes, and so what's going to be included, right? It's going to be all the nodes, right, that will be processing. So just like we've been doing in the other problems, guys, right? And then we're going to add the root to the queue, right? To start it off, right? We need something started off, guys, right? And then we have a depth variable, right? Starting at 1, right? A depth of 1, right? And then we do while the queue is not empty, right? We're going to be in this while loop, guys, right? Okay. And then what we're going to do, we're going to get the size of that current level, right? That's what we're doing, guys, right? Just like we do in the other problems, right? Okay. After that, we're going to loop through all the nodes for that particular level, okay? So initially, the queue size should be 1, right? Because the root node is the only node at that particular level, okay? AI is less than I is less than size I plus plus, okay? And then we're gonna take the nodes one by one. Do that poll. We take one node out, and then what we're gonna do, we're gonna check. Let me get some space for us, guys, right? We need some space to work with, right? We take it one by one, and we check if the node is a leaf node, right? All right, we check by checking if it has no children, right? That's what we're doing here. And if that's the case, guys, we return the depth right here, right? Because yeah. And then if it's not a leaf node, and we're gonna visit its left. It's left and right child, right? So if it's not null, then we're gonna add it to the queue. Okay. That's essentially what I'm doing here, guys, right? And then we do the same check here for the right side, right? Right side is not null. Then we visit it, right? Okay, cool. All right, and yeah, after that, we visit all the nodes at that particular level, right? To go on to the next level, right? We increment the depth variable, right? To kind of, say that we're going to the next level, right? So we visit all of, we add 9 and 20 to the queue, right? Because they're not null. And then we increment the depth, right? And then now the depth should be 2 now, right? And then once we get to 9, we take 9 out of the queue, and we do this, right? And then we can return that right away, guys, right? And then, you know, we shouldn't get there, right? But if we do, that's bad, right? The code looks good, so let's do a couple of null checks real quick. The root is null. Then return 0, right? Yeah, pretty simple. Let's press run code, see if we, you know, all right, looks good so far. Press submit. Awesome, guys. We're able to pass all the test cases, guys, right? So if you guys found value in this video, let me know that in the comment section. If you guys are new here, make sure to subscribe because we'll be doing a lot of other videos just like this one. So I want to thank you guys for watching, and I'll see you guys in the next video.